see if I can change this around. Okay. Right, everybody got number 1, that it's not going to be bounded, but it is bounded below, above, below. Go back to drinking coffee.
I think number 1 was the same question.
It is, right.
Yeah, okay, yeah.
It doesn't matter that you change it with Q. Okay. Let's see.
It's okay, Joe. Go back and do the privilege. You'll get it. I'll see it. No, right. Don't do those things. So SN is right? Yeah.
So set is bounded if it's bounded above and below. So for the set you guys just got, it's not bounded because it has to satisfy both. If a set is not bounded, then we say it is unbounded. So with math, we precisely define everything. It just has to be. So sometimes when we go into other sciences, it's difficult to communicate because we demand that of our own discipline. So if you go to another discipline, like I'm in nutrition, that's a very soft discipline compared to math. I think they call math the hard sciences. That's because we're really rigorous about how we write things. But when we look at something like, which not in class, like when they talk about unprocessed foods or processed foods, then I ask for a definition. I think I've told you this before. What's the definition of processed foods? It means that it's not in its natural state, something's been changed. So then baby food is processed food. I'm like, well, I don't really mean baby food. That's okay, so you don't mean baby food. So what is the precise definition of a processed food that you're using in your mind? Can you write it down for me? So that can be a little annoying coming from a different discipline, but if I'm thinking about the math side of things, I want to have a very clear definition of what it means to be processed if I'm writing a paper on processed foods. So I think it's a good marriage. Sometimes there's a bit of annoyance and friction between the two. And you'll find that with physics too. You'll come in and say, have you proved this or have you done this? Have you made sure that Runge Kutta actually works for the example that you took down? So did you the Runge Kutta, if your numerical analysis requires the right-hand side of your differential equation to be continuous. If you have a discontinuous function, all the theorems that are written about Runge Kutta don't work. And so you could start to ask these questions, and it can be pretty annoying. For the other team, not for us. We require it. So I'm going to give you a more formal definition of Sup and Inf. Supremum and infimum. So if I have a non-empty subset of R, the reals, I have to always say non-empty. Again, I think you learn your precision in real analysis. If there's any class that you learn that to be really precise, it's there. Nothing sloppy about it. Then the sup of S, we write this. it's a two-part definition. The first is that the soup has to be an upper bound of your set. And the second part is that if there is another upper bound, then your upper bound as a soup is going to be smaller. So it's the best upper bound that you can possibly get. So the way I think of it, and I'm going to show you some graphs. Hopefully this place will be revitalized after we get back and I can plug in. But I'll show you some graphs in Excel. It's kind of like the soup's a limbo bar. It doesn't have to be the max of a set. It's a limbo bar, and then all the elements of the set go under that limbo bar, and it's like that's as far as the limbo bar can come down. So you have a whole bunch of bars that are upper bounds, but then you squeeze that bar down as low as you can, it's going to be the best upper bound. Does that make sense? These things always make sense. I think once you start working proofs, it starts to like, oh, maybe I didn't quite understand that. Okay, questions? Inf is the other direction around, so the inf will be the smaller on the, it'll be like not a limbo bar, it's something you jump over, a hurdle, I guess. So it's like a bunch of hurdles are below your set, and then as you raise the hurdle up, the infimum is going to be the best one of those hurdles that doesn't touch the set, but actually is below the set. The reason we use sup and inf is if you have a bounded set, you're always guaranteed to have a sup and an inf, but you're not guaranteed to have a max or a min. And so this allows you to say, as long as you say, let S be bounded, then blah, blah, blah. So the kind of theorems you end up proving with this are, if I have a bounded sequence, it must have a convergent subsequence. It requires sup and inf.
Now on a graph, are you able to visually see the difference between sup and the upper and lower bounds?
Yes. I actually have, if you look at the back side of the thing that I have there, I'm going to show you some Excel graphs and you'll see where actually you
Okay.
plug in the epsilon values and you'll actually see what they are. Does everybody have this down? Almost? So keep my non-empty set. This is like the second part. You have a part B. So it's a value W that's in R such that W is going to be less or equal to S for all S belonging to S, and so it's a lower bound. If I have a V less or equal to S for all S belonging to S, then W's got to be better than it. So it's the same definition, but twice. Everything works around. I remember in real analysis I think it was last year, Alma Cooper, Dom, Trent, you know these folks. I showed them a proof with something with sup, and I asked them to prove it with inf, and it turned out to be really hard actually to do the inf direction. The inequalities all are in the opposite direction. So it wasn't just a copycat of the proof I gave on the board for sup. Okay, got 5 more minutes, right? Almost. Almost.
One more.
Right. What?
That's it.
Class, man, that's
Yeah,
it.
okay, all right.
I'm the happiest person 24 hours.
Is that a V? A V is
V,
less-
yeah, so it's,
That
if
is
you have
less
any
than-
other lower bound, this lower bound's gotta be the best.
I I'm the happiest person service there,
I think V is less than or equal.
so.
So your first sheet, turn it in, The second sheet, keep it. We're gonna continue it on. Keep it somewhere safe. Don't take it back for Thanksgiving and show off to all your family and friends. Keep it here so you don't lose it.
I would never.
It's a great way to stop politics talk at the table. Let me show you my in-class assignment.
Maybe it's my job to bring it up at the table.
Yeah, that's what I'm saying. I just start talking about politics for living at Thanksgiving. Everyone loves it.
Lovely.
Jazz politics and religion. The order that makes most sense.
That's how I don't know how I got so lucky. Because like for a while there, it's not looking good.
I think it's just like
Now
a.
it just feels good.
So Zoe had a question about that too, so I'm not gonna kill anything off on it, so I'll look at it on my own and come back to you. Alright?
We got worksheets to turn in. Yeah, the problems would be like if I'm gonna like send you a message, be like, hey, is this really I haven't chosen one yet.
Okay.
I was
If I
gonna
had
do
to do
research
revision
today and tomorrow. That's okay.
Yeah, I can
I mean,
give
I
you
did
the
revisions
ideas
like
that
a
you
while
like
ago.
to
I
do
just never
with
remember.
computer stuff.
Mm.
If you
That's
like
what
to
the
do
ones I was gonna do, just like-
Yeah, I think it's like the best,
Is
easiest one
less than-
possible to do.
I'll text you, man, as long as it's okay.
Right, yeah.
Mem,
Alright.
I think you get a Ramsey number.
Yeah, Zoe, it's a pretty
Yeah,
fat
it'd be fun
rubric.
to work with, you know,
Just like drawing.
for,
This last one.
Yeah, I'm gonna look at it.
um,
At least the here should be the green card.
So I think, do you like computing
Yeah.
too?
I've also, I did a little bit, I did like an interface simulation where you use the graph to kind of visualize the data. It's like, I used some packages from Python, so I think we could just